Good morning to all of you. I welcomes to all in our lecture series on quantum mechanics. In this lecture we are going to discuss on classical probability density and quantum mechanical probability density of a linear harmonic oscillator. So before we have to start this lecture, I am just going to be with quick revision or quick a recap whatever we discussed in the last three videos regarding this harmonic oscillator. So in our last three video we have been discussed in first part of one dimensional linear harmonic oscillator. We discussed up to eigenvalue, how what are the eigenvalues by using power series solution. All the things we have been discussed in detail, you have to go for that. And we found that eigenstates of harmonic oscillators are not continuous, these are the discrete. These things we found, and by using the Hermitian differential equation, we found the corresponding eigenfunctions. Each eigenvalues or each eigenstate, the corresponding eigen functions will be there. And in part 2 we have been found all the eigenfunctions or corresponding eigenfunctions. First state, second state eigenfunction, that is this is third state, fourth state eigenfunctions, and these eigenfunctions can be represented like this. So this is your potential curve, potential energy curve, and we found that eigenfunctions as represented like this. That means at x is equal to 0, the particle will be probability will be more for this first state, but in case of second state it will be less. In third state it will be maximum, but it is in negative. If we are going to consider probability density graph, this is the imaginary term, this is the real term of the wave function or eigenfunction. But if we are consider the probability density, that will be psi star into psi, or the so called psi mod square. We can found for first state or for 0 point energy state, the probability of finding the particle at x is equal to 0 is maximum. But for the second excited state, at x is equal to 0 is minimum, but here and here is maximum. But n is equal to 2, that means third state at x is equal to 0 is maximum. Then for n is equal to 3 is minimum. See here you can see for n value is even 0, 2 and 4 also you can consider, the probability density at x is equal to 0 is maximum. This is one observation we can found from the probability density graph. And also another observation we can found, beyond the classical limit, means here up to this much distance, the classical particle can be moved. The classical particle can be moved up to this much distance. Suppose we are going to consider this much distance, that is x, and the restoring force will be induced in such a way that if we have to displace this particle from here to here, the maximum restoring force will be produced inside that spring, and maximum displacement will be this much. For first for x is this much, for x is this much, the maximum potential energy will be this much. That means force induced inside the spring will be same, accurate will be this much. So particle could not be moved beyond of this one. But in case of quantum mechanical, particle can be moved, or probability of finding the particle beyond of this potential will be there. Means this is the significant or signifies that there is some probability of finding the particle beyond the so called classical limit. Or what are the expectation of the classical by the theory of classical method, what are the expectation beyond that particle can be also available in case of quantum mechanics. That will be called as the quantum mechanical tunneling, that we are going to be discuss. Quantum mechanical tunneling, okay, that word you just listen, and that tunneling effect is going to be discussed in our preceding classes. So then we have been discussed in the third part of this discussion. We discussed a problem that at the 0 point energy we don't have any type of rest state. We don't have any rest state, means oscillator cannot be rest. It will be always in fluctuate and obey the uncertainty principle with a derivation. This is I written in the question form because occasionally it is asking in your exam like this, but with the derivation in detail we have been discussed that yes, at for the ground state we can found del x plus del px into del px will equal to h cross by 2. Okay, now today we are going to discuss about classical probability density and yes, another thing I forgot that here, if you have to move higher to higher state, you can found one thing that the probability density is increases at the corner side and the probability density decreases at the middle. See, this is increases, this is increases. If you have to move higher n, then you can found like this, at corner it will be higher, but at center it will be minimum, right? So if it will be so, if it will be behave so, then at higher value of n, the classical harmonic oscillator will be behave as a quantum harmonic oscillator, or classical prediction or classical result will be matched with our quantum mechanical results that we are going to be discuss in today's class. So according to the definition of classical probability, that is the classical probability of finding the particle performing SHM between the position x and x plus dx from its equilibrium position is the ratio between time with which the particle takes to pass over the distance dx to time period of the oscillation. That means suppose we have to consider this is the mean position of the particle, and this particle, suppose this is a pendulum, and this pendulum is oscillating like this. This is its right hand side highest position, this is left hand side highest position, and this is oscillating like this, and it's a mean position. So it is oscillating like this, and its time period is t. Now here according to definition, suppose we are going to consider here from this origin, from the mean position, this much distance is dx. Okay, so the ratio between the time taken of the particle to cover this much distance by total time period will be nothing but called as your classical probability density. Here you can see that this particle is moving from the origin and to the highest position, again come back and passed through the origin going to the highest position like that. Okay, and its corresponding time period is this one. Let consider to covering this distance, moving this side and this side, means for one oscillation. See, suppose this is our starting point. Suppose this is our starting point. From here you drag this ball and you just lift, and it will be move like this, That means if the ball is moving from first position, second position, third position, again third to second to one, it will be called as one oscillation, that is your time period t. Where it has been started, it gone and coming back to the same position is nothing but called as one oscillation. If this ball starts from here and moving to this side, this much distance, again coming back to this position, that is nothing but called as this is not called as the oscillation, this will be called the one vibration. Starts from here, gone to highest position, and again come back to its original position, and again gone to the highest position and again came to the original position, that will be called as the one oscillation from here to here and here. That means you can say that one oscillation means it has to be touched with two highest positions. So it starts from here, it gone to this highest position, again came back to its highest position. Okay, so that is called the time period t. You just imagine that if it is in to and fro motion, it is gone this side and came back. So to covering this distance means how much distance? That will be 2x distance. Okay, in one oscillation this ball is covering this distance, means for one oscillation it is covering 2x distance. If we are going to consider this distance for one oscillation, this is dx distance, right? Suppose dx distance for one oscillation, it will be dx plus gone dx and coming back time another dx it will cover. So it will be 2x distance. Suppose 2x distance it has been covered in dt time, in dt time. Suppose dx distance, suppose dx distance it is covered in dt time, so for one oscillation to cover this distance for one oscillation, actually if this ball is moving from this to this, dx distance, let it is taken the time is dt. For one oscillation, how much time it will take? For dx to moving forward, it is dt, and backward another dt. dt plus dt is equal to 2 dt. Okay, so that means for one oscillation gone from here and came back to here, for one oscillation that particle spends time 2 dt in between this range, in between this distance. Okay, whenever time period is this one. Okay, for time period is this one, the particle presence in between this point to this point or in a short distance dx is 2 dt. Whenever the particle time period that is moving from here to here again coming back to here, time period is t1. For time period is t1, the particle spends, carefully you have to listen, the particle spends the time in this region, in this dx region is how much? 2 dt. Okay, for one time period it will be 2 dt by t. This will be nothing but is called the density. Always density means mass per unit volume, like that, mass per unit volume. So whenever time period is t, the particle spends the time in between this distance is how much? 2 dt. For one time period, how much time it will be spent in this range, in this distance will be 2 dt by t. So if this will be increased, that means the spending time of the particle in this region will be more. That means, or we can say the probability, classical probability, how much we found this one? If 2 dt will be more, by any means, if 2 dt will be more, this classical probability also will be more. Okay, so here by considering the spending time in a particular region, we can calculate the probability density or the so-called classical probability density, right? Now, so as per the definition, we found the ratio between the time with which the particle pass over a distance dx to time period of oscillation, that is t. time period of the oscillation t. If the particle passes dx distance in time interval dt, then the probability, then classical probability, just write here, classical probability, classical probability rho x class CLSS subscript class x dx is given by how much? Rho class x dx, class is in the subscript, x dx equal to time taken by the linear harmonic oscillator to pass over dx means dx distance divided by time period of the oscillation. Okay, so that equal to 2 dt, what I discussed, 2 dt by t is the total time period of the oscillation. So 2 dt by, we know that t is nothing but 2 pi by omega, so it will be omega by pi into dt. But the displacement in the form of for a linear harmonic oscillator, we know that x equal to a sin omega t, dx equal to a omega cos omega t dt, and omega t dt, it can be represented by, it can be written by dx by a cos omega t, just taken this side. So omega by pi dt will be pi, here I am dividing pi, and this side also I am going to divide pi, because I am trying to communicate this term with this one. Okay, here we have omega by pi into dt, so only for that here I divided pi, can be so it can be easily communicate this term with this term, right? So omega by pi into dt, it will be dx by pi into a cos omega t can be written as 1 minus sin square omega t. So it will be equal to dx by pi into, take a this side, inside the root over, it will be a square minus a square sin square omega t. So a square sin square omega t will be x square. So instead of here you take inside this root over, it will be how much? It will be a square minus a square sin square omega t. So a square sin square omega t is nothing but x square. So a square minus x square. But total energy, we know that half m omega square a square. We know that half m omega square x square is the potential energy. But at the highest position, there is no kinetic energy, only potential energy, or we can say that the total energy will be half m omega square a square. Let it is equation number 1. Don't write these pencils things whatever I am writing at the time of explanation, because whatever I am explaining, those explanations all will be in the video, so no need to write. So that omega by pi into dt will be equal to dx. See, dx by pi, instead of a square, I can write see 2e by m omega square, okay, minus x square. So rho x dx, see rho x dx is nothing but omega pi into dt. So rho x dx will be equal to this much, dx by pi into root over of 2e by m omega square x square. This is the classical probability density. Let this is equation number 2, right? At x is equal to 0, x is equal to 0 means what? This is x is equal to 0. X is equal to 0 means at the mean position. At the mean position, the value is how much? See, at x is equal to 0. See, at x is equal to 0, this is PCX. This value is called the classical probability density. Will be nothing but dx by pi into root over of 2e by m omega square. That is written over here is minimum, right? But at x is equal to plus or minus a, either plus you have to consider or minus you have to consider. Both, at both the point, it will be infinite. From the equation number 2, it can be found. See, if we have to consider x is equal to a, x is equal to a means this is the highest amplitude. This side is highest amplitude, this side is highest amplitude. Suppose either you have to consider plus a or this or minus a. Will be how much we can get. See, x is equal to a. X is equal to a means this will be a square. A square means 2e by m omega square. Here 2e by m omega square minus 2e by m omega square. This will be the denominator of term will be 0. So we can found rho x dx, or this will be also written as p classical into x. Probability density classical. Okay, p classical. In the next page I have been written in that format. So at x is equal to plus or minus a, PCX. PC means belongs to classical. Okay, x equal to infinite, that is maximum. From equation number 1, what we found from above two cases. From above two cases, what we found? We found that at mean position where displacement is 0, the probability of finding the particle per unit length is minimum. Here at x is equal to 0, probability is minimum. Okay, that means x is equal to 0 means this one, this is the mean position. So this is, if this is your oscillator or simple pendulum, then at the mean position the displacement is 0, or you can say this will be the mean position, the displacement is 0. Always at the mean position displacement is 0. So at the mean position where the displacement is 0, the probability of finding the particle per unit length is minimum. The quantum mechanics, that means here displacement is 0, that means I can write at x is equal to 0. At x is equal to 0, in bracket you can write at x is equal to. But the quantum mechanical probability of linear harmonic oscillator is how much in general we found already, that is psi n x mod square. You can check, previously we found that much. Yeah. This much. If psi n we are going to take this one, then psi n star into psi n mod square, psi n star into psi n will be this much, this value mod square, means this root over will be cancelled out, and this hn square we are going to be consider, or hn star into hn we are going to be consider, or h alpha x will be considered, and it will be e to the power alpha square by alpha square x square by 2 into e to the alpha square x square by 2. It will be e to the alpha square x square only. So quantum mechanical probability, this is nothing more psi n x mod square, root over is not there. See, here is root over is not there, and hn x, this is hn alpha x square into e to the power minus alpha square x square, right? For n equal to 0, alpha n mod square is maximum. You put n equal to 0. If consider this, here from this equation, let this is equation number your 3. From this equation number 3, you can understand or perceive easily. You can perceive or you can found easily one thing, that this is e to the power minus x square term. That means with increase of x, this value is decreases. Okay, that means it is one type of Gaussian behavior. See, e to the power minus x square, and this is along x-axis, positive x-axis and negative x-axis. You put the value of x, increase the x value. At x is equal to 0, this will be 1, right? You increase the x value, it will be decrease like this. It will decrease like this. Means at x is equal to 0, this value is maximum. But with increase of x, this value is decreasing. this value is decreasing. As this value is decreasing, hence this psi n x square also is going to be decreased, right? Okay, so for n is equal to 0, psi 0 square, here psi 0 square is maximum at x equal to 0, but it decreases on both the side of x, which contradict the classical probability result. Here one thing you have to be just focus, that at x is equal to 0, quantum mechanical probability density is maximum. Okay, but x is equal to 0, at x is equal to 0, classical probability is minimum. This is contradicted with each other. That means if we are going to draw the figure of both classical and quantum mechanical probability density, this is the so-called quantum mechanical probability density, that is first state for n equal to 0. At x is equal to 0, this is maximum, and it is decreases towards its highest position, and this side highest position. This is nothing but called as psi 0 mod square. However, at x is equal to 0, classical probability density is what? Minimum. But at x is equal to a and minus a, the probability density is maximum. That means plus a and minus a, this dotted line is represent the classical probability density. At plus a and minus a, it is tends to infinite, but at x is equal to 0, this is minimum. Okay, likewise it is just reverse if we are going to consider the quantum mechanical oscillation. In case of quantum mechanical oscillation, for n equal to n, then at x is equal to 0, it is maximum, and it is decreases to the both the side. Now we have to consider the same thing, it is written, but it is found that for large, now this is n equal to 0, this is the representation, that is for n equal to 0, but it is found that only for that this is the important, and I written in the red. I suggest here once again that in each video I am suggesting you that after video you have to watch, after video watching you have to write your note by pause the video. You pause the video and you have to write down the note perfectly, because always note is useful at the time of exam. But so now here but it is found that for large value of n, both classical and quantum mechanical probabilities will be matched with each other, which is represented in figure 2. See, now we have to consider n is equal to 1. Okay, so previously already we have been discussed about for n equal to 1, the corresponding eigenfunction is this one, and its corresponding probability density distribution is this one. That means at x is equal to 0, this is minimum for n equal to 1. So for n is equal to 1, this is represented by like this. Okay, at x is equal to 0, this is minimum, and like this. Now for n equal to 2, you can see at x equal to 0, the amplitude is this much, but at the two end, the probability density amplitude, this is the probability density amplitude or probability density value at the two end is increases. If we are going to draw, suppose psi 2 is how much we got the psi 2 value is this much, right? Psi 2 value, previously psi 2 mod square we have to find out, that it will be pi by how much, pi by 8 pi root over alpha by 8 pi root over that will 4 alpha square x square minus 2 square into e to the alpha square x square. If we are going to draw that one by taking alpha is any constant, then we can found this type of graph, means this type of graph we can found, but this two side will be a large peak value as compared to this one. Okay, likewise if we are going to consider 10, n equal to 10, see another thing is that, see for n equal to 0, half portion is this side, half portion is this side. Okay, for n is equal to 2 2, for n equal to 2, n equal to 4, I not n equal to 2, one peak is this side and another peak is this side. That means n minus 1 peaks will be this side and this side. Okay, and for n equal to even, at x is equal to 0 there is a value, but for n equal to odd there is a 0 value. Probability density will be 0 for this state. So for n equal to 2, this will be maximum, and this side one peak, this side one peak is there. Okay, likewise if we are going to consider n equal to 10, that means 10 by 2. Here n equal to 2 means n by 2 means 1 peak is this side we can found, 1 peak is this side we can found. Like that, if n equal to 10, if we are going to consider n equal to 10, then this side we can found 5 peaks, and this side also we can found 5 peaks, but in this manner, means at x is equal to 0 the probability density will be decrease continuously, and higher n value for n equal to 10 it is decreases, and continuously right side and towards this side, towards end of the maximum amplitude, towards the left of the right of the amplitude, maximum amplitude, left of the maximum amplitude, the probability density increases, and we are going to get the 5 peaks. If n equal to 10, we can get 5 peaks in each side. Here 1 2 3 4 5, here also 1 2 3 4 5, right? Okay, for n equal to odd, then we can found for n equal to odd, we can found n plus 1 peaks, sorry, n minus 1 peaks, this side and this side. See, no. Actually, for n equal to odd, we can found n plus 1 by 2 peaks. See, for n equal to 1, n plus 1 by 2, that means n equal to 3 plus 1, 4 by 2 will be 2 peaks this side, 2 peaks this side. For n equal to 1, 1 plus 1, 2 by 2, so we can get 1 peak this side, 1 peak this side. But in case of n equal to even we can get n by 2 peaks of this side and this side. Okay, n by 2 peaks means half portion will be this side, half portion will be that side. So if 10 will be this one and this one. Now you just watch carefully that now you consider that instead of n equal to 10, we are going to consider n equal to 100. That means 50 peaks this side and 50 peaks this side will be present. Okay, 50 peaks this side and 50 peaks this side. Now if I am going to be adjust 50 peaks in this side, then what type of graph? You just imagine the graph will be equivalent to like this. Okay, see, 50 peaks means this 0 is going to be decrease. That means it will be very closely spaced. Means I am going to say you like this. If we have to consider 100 peaks means 50 peaks this side. I could not be draw here, but it will like this. You just followed. Okay, 50 peaks means you just consider 50 peaks this side, 50 peaks this side, very closely. Very close means it will looks like this one. This means this behavior is equivalent to your classical behavior, whatever we drawn in the dotted line. So here the same thing I have written from figure 2a to b. B to b means px versus x for n equal to, and c to c is px versus x for n is equal to 10. And from figure 2a to b to c, it can be observed that as n increases, probability density px increases at x is equal to plus or minus a. So at x is equal to plus or minus a, probability density increases, this side increases and decreases at x is equal to 0. At x is equal to 0 it is decreases. Okay, if this side is going to be increases and this is going to be decreases, and then this indicates that for large value of n, that is for higher energy state, both classical and quantum mechanical matches with each other. That means if we are going to consider 100 nth excited state, what will be the behavior or probability density of the particle for nth state? Now suppose a particle is oscillating in the oscillating potential, and for its n is equal to 100th state, it will be behaves equivalent with the classical particle. That whatever we discussed and we observed. That means 50 peaks this side, 50 peaks this side. If we are going to draw closely with decreasing amplitude, it looks like this one. It looks like this one. Okay. So this is both. It is both classical and quantum mechanical probabilities matches with each other at higher states. So this is all about your classical probability density and quantum mechanical probability density of linear harmonic oscillator. So I suggest to you that each steps I discussed, so you have to pause the video and you write the note after watching this video. So thank you so much for watching this video. If any doubt, you can ask me. We have to discuss. Thank you so much. Thank you.